Alright, so let's take a look at some periodic trends among the elements on the periodic table. And as you can see, well, here is the periodic table. Just to remind you, you've got your group 1 metals, which are called alkali metals, your group 2 metals, which are called your alkaline earth metals. Moving over here, we've got group 3, group 4, group 5, group 6, group 7, and group 8. For the most part, these are your non-metals, although you have your semi-metals kind of over in this stair-step line, if you remember. And a lot of the metals in here along the semi-metal or the metalloid line are those that you would see used in like technology, cell phones, computers. You know them as semiconductors. And so here are your transition metals, your lanthanides and your actinides. Remember, the lanthanides begin in period 6. The actinides begin in period 7. Group 7 is called the halogens, and of course group 8 is the noble gases, and they have a stable electron configuration. Again, to remind you, if you're in group 1, you're going to give up 1 electron. Group 2, you're going to give up 2 electrons. Group 3, you're going to give up 3 electrons. Group 4 can act shady sometimes, but group 5 will gain 3 electrons, group 6 will gain 2 electrons, group 7 will gain 1 electron, and the noble gases are pretty much stable. And so I think that's pretty much everything here that you're expected to know in the periodic table. And again, this will help you as far as remembering which groups on the periodic table give up or gain electrons. And so there you have it there. Now we're going to think about the idea of electrons, and we're going to break it down even further into the idea of a core electron versus a valence electron. So here's what I want you to think about. Picture an atom. You can picture a Bohr model. That's just fine. And of course, you know in the center of the atom, you've got the nucleus, which contains the protons and the neutrons. Now for today, we're only going to be concerned about the protons in the nucleus. And then if you're imagining the Bohr model, then you realize that you have got all of these circles, these orbitals that are outside the atom, and that's where the electrons abide. Now you know from the current model of the atom, represented by the Schrödinger equation, it's not perfectly circular orbitals, but this idea helps get this concept across quite well. You know the definition of a valence electron is the outermost electron. So for example, if you have a Bohr model with 3 shells, that is 3 orbitals, where the electrons could abide, it's that third orbital that's furthest away from the nucleus that you would call the valence electrons, the outermost electrons. However, the electrons that abide in the first 2 orbitals you would call core electrons. So the difference, valence electrons are the furthermost out electrons. The core electrons are those in orbits closer to the atom. So there's kind of your idea there. So again, valence electrons are the electrons in the outermost orbital. Core electrons are all of the other ones that are not outermost electrons. In multi-electron atoms, the electrons are simultaneously attracted to the nucleus, but repelled by each other. So you've heard the phrase opposites attract, right? So electrons that have negative charges are attracted to the protons in the nucleus that have a positive charge. However, at the same time, the negatively charged electrons, since they have the same charge, they repel. The valence electrons, or the outermost electrons, are what we call shielded from the protons by the core electrons. So I'm going to skip some of these bullet points and let me pull up 2 examples. And so, see in this drawing here on the left where the mouse is, take a look at the 4th orbital here. The 4th orbital has 1 valence electron. So this is the valence electron orbital here. But notice you also have the 1st orbital with electrons, the 2nd orbital with electrons, and the 3rd orbital. these are what we call the core electrons, right? They're not the outermost electrons like this one here in this fourth orbital. So that's what we mean by saying the valence electrons are shielded by the core electrons. These core electrons here in this first, second, and third orbital are in the way of the valence electrons because they're so far out. And let's see if you can kind of pull the idea together. You know, the positively charged protons are located here in the nucleus. And these valence electrons that are so far away have a negative charge, but opposite charges attract. And so these valence electrons here want to feel that positive attraction from the nucleus, but there's a problem. They can't feel that attraction very well because all of these pesky core electrons that are in the way. And that's kind of the basic idea for here. And so here's another curious idea. As you go across the periodic table, so that as you go from the left-hand side moving directly to the right-hand side within a period, you only add valence electrons and not core electrons. So here's the idea. Say you're in period 4 here. If you go from potassium all the way to krypton, but you stay in this fourth period, you're not adding any more of these pesky core electrons that are preventing the valence electrons from feeling the positive attraction from the protons in the nucleus. That's kind of the idea. You're only adding valence electrons. So think of valence electrons as the good guy. Or you can think of it this way. Think of the valence electrons as a guy and the protons as a girl. And the guy is trying his best to get to the girl, except you've got all these pesky core electrons getting in his way. Every time you go across a period, you're only adding the good guys. And you also add more protons when you move from left to right, which is a good thing also. So the idea as you move across a period, you're adding more good guys, which are good valence electrons, and you're adding more protons, which is more positive charge, more of an opportunity for the good guys, the valence electrons, to feel attraction from the nucleus. But still, you've got these pesky core electrons in the way, and they're keeping the valence electrons from feeling all of the attraction that it wants to from the proton or the girl in the nucleus. So if you look over here on the right, you've got 2 valence electrons here in this fourth shell, and it wants to feel that positive attraction from the protons in the nucleus. But all of these dumb core electrons are in the way, and so this valence electron can't feel all of the positive attraction that it wants to from the protons in the nucleus because of these pesky core electrons getting in the way. This is kind of the basic idea behind effective nuclear charge. This results in the valence electrons and protons becoming more strongly attracted. That is, when you go from left to right across a period on the periodic table, because you're adding more good guys, the good valence electrons, and more proton, more opportunity for the valence electrons to feel that attraction because you're adding more protons, more positively attracted particles. And so, my friends, this leads us to the place that your teacher is more than likely perpetually stuck for the rest of his life, and this is called the friend zone. And so I had a student in class, my very first trimester of teaching, that drew this picture for me in his notes and gave me a copy of it. And so here's the idea. Here is the guy who is in the outermost orbital, so he is the valence electron. Here is the nucleus, the protons, and here is the girl that he's very attracted to. And so this valence electron, which has a negative charge, wants to feel the positive charge from the girl in the nucleus. But they're really far apart, right? Because he's in the valence shell. And then you have these evil core electrons, right, which are her girlfriends, that are blocking him from feeling that positive attraction from her because they're in his way. They're in between. So the idea of effective nuclear charge is that as you move across a period on the periodic table from left to right, you're not adding any more of those evil core electrons. You're only adding more proton, so more positive attraction, and more good valence electrons. And that's why when you move from left to right on the periodic table, you will see that the attraction becomes stronger. And so here's how you can equate that in this drawing. As you move from left to right on the periodic table, you get more of the good valence electrons, you get more of the positively charged protons, and that kind of squeezes these pesky core electrons out of the way. And so the valence electrons and the protons can become closer together. They're more attracted, so they get closer together. That's effective nuclear charge. But let's take this idea a step further. What happens when a man and a woman become close? Well, when they get closer together, well, there's less space in between them, right? So when you get more of the good guy, the good valence electron, and more of the positively charged proton, that causes these two to become closer together. And that, my friends, is how effective nuclear charge, which increases as you go from left to right on the periodic table, affects atomic radius. Because you have more valence electrons, good guys, and more protons, and they're coming together, that's reducing the space in between them. And that is why, as you move from left to right on the periodic table, the atoms become smaller. More protons, more good valence electrons. You're not adding any more of those evil core electrons, and you have positive and negative charges becoming stronger, becoming closer together, and therefore shrinking the distance in between them. That means they're shrinking the size of the atom as you go from left to right. So that's how effective nuclear charge and atomic radius work together. And finally, as you go down a group on the periodic table, you can see that the atom is becoming larger. And you know that because every time you go down a group, that is down a period, you're adding a shell, right? So here is n equals 1, n equals 2, n equals 3, n equals 4, n equals 5, etc. And as you do that, according to the Bohr model, you're adding a shell every time. Or according to the electron configurations, 1s, 2s, 3s, 4s, 5s, etc. Left to right on the periodic table, the atom gets smaller due to effective nuclear charge. Top to bottom, the atoms get larger due to adding more shells, and that's atomic radius. Let that soak in just for a minute. Let's move on to another idea that is, to me, just as simple, and that's ionic radius. So think about it. We reviewed at the beginning of the video, and you guys know that group 1, group 2, and group 3 give up electrons. Group 1 loses 1 electron, group 2 loses 2 electrons, and group 3 loses 3 electrons. And so the blue represents the size of the original atom before it's lost any electrons whatsoever. The gray represents the size of the atom after it has lost an electron. So, for example, here's potassium. The size of a potassium atom is this blue, but the size of the potassium atom after it's lost an electron is much smaller. That's the idea of ionic radius. When you lose an electron, like group 1, 2, and 3 metals do, the atom is going to become smaller because you're losing something. Now, take a look at group 5, 6, and 7. The red is the size of the atom before it gains electrons. You guys know these three groups, 5, 6, and 7, gain valence electrons so they can become like a noble gas, right? Which is the reason these lose valence electrons also, to become like a noble gas. But here's nitrogen before it's gained 3 electrons in the red, and here's nitrogen after it's gained 3 electrons to have an electron configuration like that of a noble gas. And so it's becoming larger when it gains an electron. So when an atom loses electrons, it becomes smaller. When an atom gains valence electrons, it becomes larger, which is pretty intuitive, and that's the idea of ionic radius. Here's an atom of lithium, which will lose a valence electron. Here's the atom of lithium after it does lose that valence electron to become a cation. Here's an atom of fluorine before it loses a valence electron. Here is the same atom of fluorine after it's gained a valence electron to form an anion. So cations are always smaller, anions are always larger. Here's another idea of a periodic trend called ionization energy. Ionization energy is the minimum energy required to remove an electron. So think about that. Ionization energy, minimum energy required to remove an electron. And this concept is so simple. Think about it. Metals already want to lose valence electrons so they can become like a noble gas. And so since metals like group 1, group 2, and group 3 metals already want to lose a valence electron, it's not going to take much energy for that to happen. And so they have very low ionization energies. However, think about fluorine or chlorine. They only need to gain one more valence electron to become just like a noble gas. So since they only need to gain one more valence electron, they sure don't want to lose one. That's going to stop all the progress that they've made. And so it's going to take much more energy to remove an electron from an atom of a halogen, group 7, because they want to gain one more to become very stable. If they lose one more, they're going to become even less stable. So they're going to be clinging on to their valence electrons as much as possible. And so it's going to take much more energy to remove a valence electron from one of these atoms here that want to gain valence electrons to become like a noble gas than it would for a metal that's going to lose the electron anyway. That is why the trend for ionization energy as far as going left to right is the same as effective nuclear charge. As you move across a period from left to right on the periodic table, the ionization energy increases. That is, the energy required to remove an electron. Ionization energy also increases as you go from the bottom of a group to the top of a group on the periodic table. And here's why. When you get so far away from the nucleus, so this is the 1, 2, 3, 4th shell. So you're pretty far on the bottom of the periodic table. The attraction, this negative attraction, as you know from effective nuclear charge, to this nucleus is pretty small because it's far away and you've got these core electrons in the way also. So these are blocking this negatively charged electron from feeling the positively charged proton. That's the idea of effective nuclear charge. The idea is you're so far away from the nucleus, there's not much attraction. So this electron could actually be lost pretty easily because it's not very tightly bound because it can't feel much of that attraction. It's kind of like a breakup. But as you get closer to the nucleus, say the first shell, it feels the attraction very, very strongly, right? It's not far away and there's nothing in between it. And so it's not going to be likely, this electron here is not going to be very likely to go away. It's the same idea with ionization energy. When you go closer to the top of the periodic table, the electrons are much, much closer to the nucleus, and so they feel that attraction much more strongly, so those electrons are less likely to be lost. But these here that are in shells so far away from the nucleus don't feel that charge, so there's not much attraction, and so these electrons are more likely to be given away. It's not going to take much energy for that to happen. And then another trend is electron affinity. Now, let me go back to the definition for ionization energy so you can distinguish. The ionization energy is the minimum energy required to remove an atom. Electron affinity is the energy released when an atom gains or accepts an electron. Ionization energy is to remove an electron, but electron affinity is the energy released when an atom accepts an electron, which is great. And so I have a stress analogy for this because we can all relate to stress in our lives. But here's the trend first. Electron affinity increases from left to right on the periodic table. So just like ionization energy, the exact same trend. So here's my stress analogy. Let me go back to a slide here that's just got the good old periodic table. So remember the definition. The energy released when an atom accepts an electron. So when you're really, really stressed, you have a lot of tension, right? Well, these group 7 halogens are very, very stressed because they only need one more electron to become stable like a noble gas. And so they're really tense. They're stressed because they're coming up with ideas to try to find one more electron so they can finally be energetically stable. So once fluorine or chlorine does gain that electron, they release that tension, they release that stress because they've achieved their goal. And so when you release stress, you might get really, really tired or something like that. And so electron affinity is the same way. These atoms here are very stressed because they want to gain an electron. But when they finally do gain that electron to become just like a noble gas and stable, they're going to release a lot of that stress. They're going to release a lot of that tension. And so that's kind of how you can think of electron affinity. It is the energy released when an atom becomes less stressed due to gaining an electron and becoming more stable. And it increases from left to right as you would expect. These want to gain an electron, so they're the most stressed, they're the most tense, and so they're going to release the most energy once they do gain that one valence electron. As you get over here in this area, these have to gain a whole lot more electrons, 1, 2, 3 more electrons to become stable. They have a lot more to go. They're kind of like that student that's somewhat motivated, somewhat not, going to take a whole lot more work to get there than one that's already right here. And think about the metals here. Well, these are going to lose electrons anyway. They're sure not going to gain them, right? And so that's why their electron affinity is very low and why it increases from left to right. And my friends, you have periodic trends now covered.